Hello and welcome back to the Enrichment series. In this episode, we're going to focus on trig function applications. So you have the six trig functions right here at the top, and the three basic ones are sine of theta, cosine of theta, and tangent of theta. You've probably learned so far in this class that you can do 1 over each of those and get the other three. So 1 over sine is cosecant, 1 over cosine is secant, and 1 over tangent is cotangent. And why do we study trig functions? They tend to model natural and physical phenomena. So some examples are populations, waves or tides, engines, UV intensity, the Earth's rotation, and there are a couple others as well. And what makes them special is the fact that trig functions are periodic, which just means that they have a repeating shape. And because of that, they're able to model things with regular cycles, just like in the examples above. You should note that tangent, cosecant, secant, and cotangent are pretty uncommon in the real world, and that's because they're discontinuous, which just means they have those asymptotes that you've probably seen. And there aren't a lot of things in the real world that would have those asymptotes, so really we just focus on sine and cosine. But I tried my best to incorporate some of those other ones in the examples. So here is a summary of what a trig function looks like, kind of the different components or parameters. And you can take a screenshot of this if you want to. But let's go ahead and start on the right here. So this is letter D, and D is going to be our vertical shift. The vertical shift just moves the midline up or down. And let me actually show you what a midline would be. So a midline is kind of like right through here. This color is kind of light, but hopefully you can see that. So it just kind of splits the graph in half, basically. And so when you have a vertical shift, it's going to move up that midline. That's pretty much it. Or down, depending on if it's positive or negative. And then you have the phase shift. So the phase shift just moves the graph left and right. And if you have a positive phase shift, that's just going to be left and then negative for right. We've seen that before. And letter B is the wave number. And it's just the factor that kind of describes the number of waves that you would have in 2 pi radians. You don't need to get too picky with wave number. It's just kind of a coefficient you need, which will basically tell you, how many waves you can fit in that interval. And then the last one is going to be A, which is amplitude, and that is how far up and down from the midline. So typically we have a default midline of 0, so there's no D right here. And so then the midline is just going to be the x-axis, and then you have some amplitude, like maybe it's 1 and you don't have a coefficient in front of here that's greater than or less than 1. So then it's going to be at 1 at a maximum and -1 at a minimum. Okay, so here's some other points that I think are pretty important to learn. So we have, first let's talk about period. So period represents the time it takes to complete one cycle. And I put like time in quotations because it's really just whatever is on the x-axis. It could be time, it could be the angle, but I guess you could say like the amount of space it takes to complete one cycle. And then it's important that we know what a cycle actually is. So I have the points drawn out on the graph here, but it's basically from peak to peak or trough to trough or middle to middle, or really just anywhere along the curve. to like the next equal spot, but typically we measure it at these 3 places. So from peak to peak is from here to here, and then right here we have trough to trough, just the bottom. And then you can even go from the middle of the wavelength, or the middle of the curve, I should say, to the other side. And so all of those are equal. These are all 1 cycle. All right. And so also that's known as a wavelength, which you've maybe heard of that before as well. And then there's a formula for period. It's just 2 pi divided by b, and b was the wave number. Frequency is 1 over period, and frequency is the amount of cycles per unit of time. So the way that I like to differentiate between the two is that period is time over cycles. So it's the amount of time for 1 cycle, while frequency is cycles over 1 unit of time. So they're just kind of flipped there. All right, the last part for this part of this episode is that we're going to do part A of this example. So this is spring oscillations, and we're going to introduce some of the basic concepts. So the displacement of a mass held by a spring is modeled by the function h of t equals 0.5 sine of 6 pi t. And then h of t is measured in centimeters and t is measured in seconds. And we have a diagram here. So when the spring is not moving, our mass is at equilibrium. It's just kind of chilling. And so you can see at equilibrium, our function equals 0. And then when we stretch it out, you would have to apply a force for that. But let's just say it miraculously did this. And at that point, the function becomes greater than 0. And we just kind of designated that. When it bounces back up and goes above equilibrium, we say the function is less than 0. So then we ask ourselves, what is the amplitude? What does it represent? Period, frequency, midline, and what do they represent? All right, so starting with amplitude. Amplitude, we said, was that coefficient in front of the function, and that's going to be 0.5. So it's going to be 0.5 centimeters. And then we also want to consider, what does that really mean in the context of the problem? So if we look here, remember, amplitude is how far up or down from the midline. So it's kind of like your maximum value above the midline and your minimum value, which is below the midline. So really, 0.5 centimeters is just going to be that maximum distance from equilibrium, because kind of our midline, you could say, is equilibrium. So I should have asked that first, but our midline is equilibrium. And then it's going to go a maximum of 0.5 centimeters above or below that. So we can say, try to write this, maximum compression or stretch. I'm gonna use a different color. Okay, and then so we also want to talk about period, and we have a formula for period. Period is equal to 2 pi over b. And we're given b in the equation. B is that multiplier in front of the variables, which is 6 pi. So we're going to do 2 pi over 6 pi, and that's going to give us 1/3. Remember what we said about period, it's time over cycles. So really this is going to be 1/3 seconds. And again, what does that represent? We know that period is the time it takes to complete one cycle, but we probably want to be a little more specific. So in this situation, it's going to be the time it takes for the mass itself in the spring to complete one full oscillation. So it's going to go down, back through the equilibrium, compress, and then back to equilibrium. So it's that full oscillation. So again, it's going to go down, back up through here, compress, and then back down. So we're going to say this is one full oscillation of the mass. All right, so then we have these last few parts here. Frequency is just going to be 1 over period, and we looked at that on the last slide. So we're going to do 1 over 1/3, which is going to equal 3, and that is the frequency. Oh, my computer almost fell. Okay, I think we're good. And so what does that represent? Remember, frequency is cycles over time. So this means that we're going to make, that doesn't look very good. Hold on. 3 oscillations in 1 second. So that's our unit time. And we kind of already talked about midline. Here, I'll kind of write it off to the side. Midline is just going to be equilibrium. We were kind of given that. The way that we know also is the fact that in the equation, there's no plus or minus at the end of it, which would be a vertical shift. And by default, our midline is just 0. So